Hello and welcome to this quick introduction of ImpulseQt version 3.1.8. This program is for doing gamma spectroscopy or gamma spectrometry for those in Europe, and it is for doing it with an audio device. So this is an audio device gamma spectroscopy program. It will work with the Gammaspectacular GS-PRO or the Theramino adapter or any homemade adapters. This program can be used with both audio devices and serial devices, but this video is dealing only with the audio device. The device selection menu is up top here in the top left hand corner, where you can choose between the audio device and the serial device, but just keep in mind that when you're switching devices you need to restart the program. The first thing we need to do is select our correct audio input. So assuming that you have your detector connected to your sound card driver and that your sound card driver is connected to your USB on your PC or Mac. So that should come up here in this device menu. You will normally see your PC internal microphone and whatever other devices you have connected that contain a microphone, but you will also see there the driver for your gamma detector, which in this case is the GS USB-PRO or the GS-PRO-V5, and that comes up as a USB audio codec. So we select that one from the drop-down menu. Okay, the next field here is the sample rate, sample length, stop condition and buffer size. So we'll go through those one by one. So the sample rate is how often the voltage from the detector gets sampled. So it ranges from 44,100 to 384,000 or 384 kilohertz. Generally, the higher the sample rate, the more accurate the pulse height can be measured and the better resolution your spectrum will have. There are reasons for choosing a slower sample rate. That might be if you're running a very slow computer or a Raspberry Pi or something like that, which doesn't have the capacity to sample quickly. The other reason might be that you want to give a preference to sample or count rate rather than pulse height. But in this case, this demonstration, we're going to focus on pulse height, so we're going to set it to the highest sample rate, but I will demonstrate how that works in a second. The sample length is the number of samples that we sample for one pulse. The stop condition relates to the number of samples that we're going to sample before we're calculating the mean average sample, and I will explain that in 1 minute. And the buffer size is simply the computer memory's ability to hold data in a buffer while it's doing the processing. I will, for this demonstration, set it to 8192 as I'm working on a Mac here and we don't have a problem with the amount of memory. So great. So now the first thing we want to do in sound card spectroscopy is to sample the pulse shape. The reason we do this is so that we can use this pulse shape, or I should say the mean pulse shape, to measure every incoming pulse for distortion. As we do not want distorted pulses in our spectrum, it will upset the resolution and we will get an inferior spectrum. So by collecting a large number of mean pulses, or collecting a large number of pulses and then calculating the mean, we can use this mean to discard badly formed pulses. And this comes at a loss of some pulses, but it improves the resolution of the spectrum. Now let me show you how this works. So we can show you here, for example, sampling at 48 kilohertz and 61 samples. We click Get Pulse Shape. So this is a pulse shape acquisition function. And here you can see the pulse shape is coming in, and here we can see that this is a fairly narrow pulse, and the baseline is fairly flat and there's not many sample points in the actual pulse itself. So although this will work, it won't give us great resolution. So let's see what happens when we increase the resolution to twice as much, 96 kilohertz. You can see straight away we have a wider pulse and we have more sample points defining our pulse, giving us a more accurate pulse. Now let's go all the way and set that to 384 kilohertz, and you'll see that we have a much more accurate pulse, and we're getting an average here, very, very smooth, differing very little from pulse to pulse. So when we are measuring the pulse height later on in this program, we will be using the lowest value of the sample and the highest value of the sample, and the difference is the pulse height. But what we're seeing here though is the normalized pulse, and what the scale on the y-axis here indicates percentage of the total sound card input. So this mean average pulse that I have now sampled, that represents about 10% of the sound card average input. The next function here is the distortion curve. So this is an interesting function because what it does is it will collect 500 pulses and it will sort them by distortion and present them as a plot. This gives us an idea about what the number of distorted pulses are coming from our detector. So let's have a quick look at what it does. It usually doesn't take long. Here you can see it's collected 500 samples and sorted them by distortion. So if I look at distortion here, the maximum distortion was 43%, and it goes down from there. So later on, if I want to determine the number of samples to filter out, I might decide to not include these heavily distorted samples in my spectrum. And I can then set that on the next page where I do the histogram. I can choose what rate of distortion I determine is acceptable for my spectrum. Okay. The only other function on this page that we might mention briefly is the peak shifter. So all that does is it shifts the peak. So if I set that to +5, for instance, and redo the pulse shape, you'll see the pulse shifts over to the right. And if I set it back to 0 and redo that, the pulse shifts itself back to the center. So this might be useful if you have a distorted pulse, or if you feel that you can get a better pulse definition by moving your pulse a bit off to one side, then give that a try, and you might get a good result from that. Now the next function on this page here that I might just briefly mention is the stereo mode, and that is only applicable if you're using 2 detectors and 2 GS-PRO units. You can in fact use this program in coincidence mode and stereo mode to run it with 2 detectors, but I will not be covering that in this video. And if any of you didn't catch everything that I said, or if I missed something, I should point out that there is a manual, a comprehensive manual on the last tab. So if you look up here in the menu, if we go to the manual here, you will find all the information about every single function, and you can look up what that function does in case I haven't explained it. And if I have missed something in the manual and you'd like to see it in there, send me an email and I will deal with that in the next version. Okay, let's move on and go to the 2D histogram, which is where we would see our regular spectrum. And I'm going to move myself just over here out of the way so we can see the functions that we are trying to work with here. So this page is the histogram, which has largely a big plot in the middle there, and it's got a number of functions below, which I'll try to cover as much as possible, and we'll see how we go. So the 2 buttons here, start and stop, are pretty self-explanatory, and below these buttons we have 2 stop conditions. So if we are running multiple spectrum analysis and we want to stop the spectrum at a specific number of counts, then we can enter that into this box down here, and for the argument's sake we can put that at 1 million counts, and stop after a number of seconds. That's another stop condition. So you might have a bunch of samples, you want to all run them at exactly 1 minute. We can set those to 60 seconds or whatever, 300 seconds, 5 minutes. And good. Now, the next field along here that you want to know before you start is the file name, and it defaults to my spectrum, but of course you can call that anything you like. You can say that this is a spectrum of moissanite or whatever. And then we have the pitch, which I'll deal with in a moment. The next thing we have here is a number of channels. So the default, it comes up with 8192, which is way too many channels than way more channels than you need. So typically for sodium iodide spectroscopy or for any scintillation spectrometer, 1000 or 2000 channels is all you really need. So I'll set it to 2048 channels. And the pitch is the arbitrary units per channel, which will depend on your voltage setting, which depends on your preamplifier setting and all those settings. So until you've adjusted your equipment, it's difficult to tell you what the exact pitch should be, but the program is designed to be around 10 to 20 is about typical normal pitch size. Then we have the next field here, which is the LLD, which is the lower limit discriminator. This discriminates the bins on the left-hand side, which is mainly to remove any ripple, preamplifier ripple or amplifier ripple that might come through in your spectrum as a tall peak in the first channel. We generally want to just get rid of those. We don't need that. Intervals is the refresh rate of the screen. So we want that, it's defaulted to 1 second here. We see the screen refreshing at 1 second. But if you have a computer which is struggling with the load, then you can set that to 5 seconds or 10 seconds or even 60 seconds. It doesn't matter. It will just reduce the workload of the computer. And then we have distortion tolerance, which should be in percentage. And we should set that to an average probably of 35%, just to see how that goes in the beginning, and we can adjust that later if we feel that the tolerance is too tight. Now keep in mind, if you set the tolerance too tight, you won't get a spectrum at all. So it'll basically filter out everything. So there's a number of other functions on this page, but I think at this stage, I think we should click the start button and see what happens. I have a probe connected to the system at the moment with no source in front of the probe. So what we'll see here is we'll see that the counts are coming in. So these represent counts on the y-axis and energy on the x-axis, but since it's not calibrated, these are energy in arbitrary units. But what we're seeing here is the pulses coming in and the counts are building up in each channel. So every time a count comes in at a specific energy, that gets sorted into a particular channel on the x-axis here. So if I go over here and get a source like cesium-137 and place that detector on the source, we'll see straight away that we're getting a peak over here coming up nicely. Okay. And it comes up pretty quickly. And we can see the total counts over here and the elapsed time over here. All right. Now, we have some other functions here that we want to quickly go through. These checkboxes on the side here. We have the common one, which is showing the spectrum in logarithmic scale. You can check that one and see what that does. We also have the energy per channel. That distorts the spectrum, but what it does, it enhances the counts on the right-hand side and lowers the counts on the left-hand side. And that's useful for seeing peaks where in the very high end there's low counts and you want to enhance that end. Then we have the calibration, which we'll look at in a minute. And we have a function here to show linearity. So in this particular spectrum, it looks like we are cutting off a little bit too much of the lower limit discriminator here. So I'm going to stop that, and I'm going to change that to 10. And so we see more of the left-hand side, and I'm just going to restart that spectrum. That will now overwrite the previous. And as you can see now, we're getting a taller peak over here, which is normal. This is the X-ray from cesium-137. I'm just going to let that run for a few seconds. And now you can see the peaks are coming up nice and clear. So now we want to calibrate this spectrum. So there's two ways to do that. First we need to select our peaks. And we can do that by simply double-clicking on the chart itself. Double-click and it'll select a region of interest. And it'll show up in the table up here. Now we know that this one here is 661.7 keV, so we can just type that in here, 661.7. And that sets that, and if I turn calibration on here, it will tell us that that is the barium 137M 661.7. Next I can select the X-ray peak over here, and I know that's about 32 keV, and we now have that calibrated. I should mention this again, we have the chart is up here in the main window, but I can pop out that table to get more visibility, and then we can see better what's going on here. So now you can see here I've selected two regions of interest. I have a table up here. I've put my energies in, and it automatically calibrates the spectrum and gives me suggestions of isotopes that might be over here, which makes it very easy to see what's going on. Now I can do a number of things here. I can dock the table back again or pop it out. I can also download the peaks. So you've taken the spectrum, you've created a wonderful table of peaks, and you want to save that information. You can simply click the download peaks button up here, and you will get a nice CSV file in your downloads folder containing all that information which is in the table, which is nice and useful. You can also, if you want to redo your peaks, you can clear the peaks simply by clicking clear, and that will get rid of everything in your table. And we also have a function to auto select peaks, and that is related to this little feature down here where you select the width of the peaks you want to select and click auto select, and there you see the program has automatically found a number of peaks in this spectrum. Now we might want to set that wider and clear that again and see what that does. And now you can see, because we selected a wider peak, it then ignored some of the other peaks it found. Pretty nice and handy feature. There is one more function here that I should mention, and that does require calibration. So let's quickly do the auto peaks again. Let's put the 32 in there. And in this case, I'll also put the 200 in there. I'll pop that table out for a second. And we'll put the backscatter peak as 200 keV. And put this one as 661.7. So now we have a spectrum here. It's probably is not exactly 200. It's probably 195 or something. I think that's more reasonable. And if I now click the show linearity button, we get this extra line up here, see? And this gives you some idea of the linearity, and this can be very helpful when selecting peaks, because sometimes we might select the wrong peak and assign the wrong energy to a peak, and this will become very obvious when you click the linearity button, because the peak won't fit anywhere. It will be completely crooked. So this gives you a reasonable idea that this is a reasonably linear spectrum. It's got the 32 keV, the 200 backscatter, and the 662 cesium-137 peak. So that's it's a handy little feature that can be used. So let's clear all that out. And last but not least on this page, we have the sigma function, which gives you the Gaussian peaks. This function can be very handy at identifying peaks which are difficult to see with the naked eye. So, for instance, here we can see them standing out, and it's probably more obvious in log scale, where you can see there is some peaks here that are virtually invisible to the naked eye, but in the Gaussian function they actually stand out much more clearly. So you can use that function to identify really small peaks. Very handy. Oh, there's a lot of stuff to cover here. We also have a comparison spectrum. So we have here a large library of gamma peaks you can choose from, and you can also choose from your own recorded spectrums. So this function is intended to be used as a background subtraction function, where you can record a clean background spectrum over several hours from your lab with no sources present. And you can use that as a different spectrum when you're recording your source. So I don't have a background spectrum here at the moment, but that's what you would do, and you would do show comparison. You could overlay the two spectra and see one on top of the other, or you can do subtract comparison, and it will subtract the background spectrum from the source spectrum, and you will see a different spectrum, which again makes the isotope peaks stand out a lot more. But what we can do here is, if we turn on calibration here and go to comparison spectrum and find cesium-137, we will see the peaks for cesium-137 overlaid. A, B, C, CS137, there we go. Okay, here you can see the cesium-137 peak overlays nicely on the peak that I have recorded here, and the little X-ray peak is visible there as well. So very neat little function. Okay, let's stop this spectrum and move on, otherwise this video will be way too long. The next page here is the waterfall spectrum, which is pretty cool. Again, we have the start and stop button. We have an opportunity to select an existing file or a new file. We'll just do a new file since we don't have any existing files on here at the moment. Yeah, so just using the 2048 channels as we did on the previous spectrum, because we're using the same calibration. So here you can see essentially this is the cesium-137 peak. If I move my detector away from the source, you can see that the spectrum disappears here, and when I put it back we'll see it coming back. So this gives you a spectrum over time, which is interesting for any experiment that requires a changing source. So where the gamma spectrum changes over time, this can give you a time-dependent graph. Sometimes referred to as a heat map or a waterfall spectrum. And once again here we have the download array, and we can also stop that, and we can view that in full screen mode, which is not going to be visible for you there. Hang on, I would need to move that in there. Anyway, I think that's, we also have the, we can display this in a log function and so on, same as the other. You should be able to find something interesting to do with that. Let's move on before this video gets too long, and on the next page we have the count rate. So this one's pretty straightforward. This works together with the 2D histogram and the waterfall histogram, and simply shows the count rate over time. There's not much to demonstrate here, because the start and stop buttons actually work from the other pages. So if we go, for instance, back to the 2D histogram, click start recording our spectrum here, and we then go to the count rate, we will then see that this is now counting the counts per second. And we have a little slider here where we can get the average counts over a certain number of intervals. And once again, we have the download CSV function and option to view previous files. So that pretty much concludes the introduction to ImpulseQt and version 3.1.8. And don't forget to look back occasionally and look for the latest version, because this software is fairly new, and I'm making updates to it quite frequently. In the beginning it's once a week, and then maybe once a month, and then after that maybe every couple of months. So yeah, by all means check the version number and go back and get the latest one. There's always something been fixed or something improved. Thanks for watching.